Ever stared at an engineering drawing and felt lost in a sea of symbols? You're not alone. Two of the most important symbols are for parallelism, two slashes, and perpendicularity, an upside-down T. These aren't just squiggles. They're critical instructions for how parts fit and function. Parallelism and perpendicularity are part of GD&T, the universal language that ensures parts made anywhere fit together perfectly. These controls don't tell you where a feature is, but how it's angled. Think of building a bookshelf. Shelves must be parallel to the floor, supports perpendicular. Without these, even perfectly shaped parts can fail if they're tilted wrong. In this guide, we'll break down what these symbols mean, how to spot them, and how to measure them in real life. By the end, you'll read those symbols with confidence. Let's get started. Let's start with parallelism. The symbol? Two forward slashes. When you see it, it means a feature must stay the same distance from a reference surface, called a datum, at every point. It's about keeping features running side by side, like train tracks. The tolerance tells you how much tilt is allowed. Imagine two invisible planes, perfectly parallel to the datum, and the feature must fit between them. For surfaces, the whole area must stay within those planes. For holes or pins, the axis must stay inside a perfectly parallel cylinder. Example: if a block's bottom is datum A and the top surface has a parallelism callout of 0.1 mm, every point on top must be within 0.1 mm of parallel to the bottom. For a hole, the axis must stay inside a cylinder parallel to the datum. The feature control frame tells you everything: symbol, tolerance, and datum. Read it as, this surface, or axis, must be parallel to datum A within X units. That's parallelism in a nutshell. Now, perpendicularity, symbolized by an upside-down T. This control ensures a feature is at a perfect 90-degree angle to a datum. Like parallelism, it's about orientation, not location. For surfaces, the tolerance zone is two planes at 90 degrees to the datum. For holes or pins, it's a cylinder perpendicular to the datum. Example: if a block's bottom is datum A and a side has a perpendicularity callout of 0.2 mm, that side can't lean more than 0.2 mm from square. For a hole, the axis must stay inside a cylinder at 90 degrees to the datum. The feature control frame spells it out: symbol, tolerance, datum. Read it as, this axis must be perpendicular to datum A within a cylindrical zone of X units. That's the essence of perpendicularity. The feature control frame, or FCF, is your GD&T cheat sheet. It's a rectangular box with compartments. First, the geometric symbol. Second, the tolerance. Third, the datum reference. For surfaces, the tolerance is a number, distance between planes. For axes, you'll see a diameter symbol, meaning a cylindrical zone. Datums are your measurement starting points, perfect planes, lines, or points. The FCF lists datums in order: primary, secondary, tertiary. For parallelism or perpendicularity, you'll often see just one datum. Example: a hole with an FCF reading perpendicularity, diameter 0.2 A, means the hole's axis must fit inside a 0.2 mm diameter cylinder at 90 degrees to datum A. The FCF tells you exactly what to check and how precise it must be. Master reading it and you'll unlock any drawing. That's the FCF decoded. How do you check parallelism? The classic way: a granite surface plate and a dial indicator. Place the part with the datum surface flat on the plate. Set up your height gauge or dial indicator to touch the controlled surface. Zero the indicator at one end, then sweep across the surface, watching for the highest and lowest readings. The difference is your parallelism error, called total indicated runout, TIR. If TIR is less than or equal to the tolerance in the FCF, the part passes. For axes or complex parts, use a coordinate measuring machine, CMM. which digitally checks points and calculates parallelism automatically. Always compare your measured value to the drawing's tolerance. If you're under, you're good. If not, the part fails. That's how you measure parallelism. Checking perpendicularity? You can use a functional gauge or a CMM. With a gauge, place the part datum side down and try to insert a pin at 90 degrees. If it fits, the part passes. For more precision, use a CMM. Secure the part. Probe the datum surface to create a reference plane, then probe the hole or feature. The CMM calculates the actual axis and compares it to a perfect 90-degree axis. The software gives you a perpendicularity error. If it's within the tolerance, you're good. Example: if the CMM reports 0.08 mm and the tolerance is 0.1 mm, the part passes. Always measure from a clean, accurate datum. Whether you use a gauge or CMM, the principle is the same. Check the angle, compare to the tolerance. That's perpendicularity inspection made simple. Let's move to common pitfalls. Even pros make mistakes inspecting parallelism and perpendicularity. The biggest pitfall: poor datum setup. Cleanliness and flatness matter. Always clean the plate and part, and check for burrs or dirt. Move the indicator slowly and cover the whole surface. Don't miss high or low spots. Watch for indicator drop at the edge. Keep the tip engaged. Use the right size indicator tip for the surface. Example: for a block with parallelism 0.1 mm to datum A, sweep the top surface. If TIR is 0.1 cm or less, it's good. For a hole with perpendicularity 0.1 mm to datum B, use a CMM to check the axis. Remember, parallelism is 0 degrees to the datum, perpendicularity is 90. Master the symbols, the FCF, and your inspection technique, and you'll guarantee parts that work every time.